Hi, my name is Vincent. I am with my classmate Avi, and we are Team 40, and we're doing our final project on mortality prediction in the ICU using the Mimic 3 dataset. This is for our final project for big data for healthcare. Okay, so I'm going to give a brief presentation outline first. First, we're going to talk about the research question. Then we're going to go into some literature review and background. Then we're going to talk about the data that we use, which is the mimic data. Then we go into our empirical design for our model. Then we're going to talk about our results. And then we're going to conclude the future considerations. So overall, what we're trying to do here is we're trying to predict mortality. So what is the probability that a patient in the ICU will die at the end of the admission or within the hospital admission using the Mimic 3 dataset? And so specifically, right, we're trying to answer the question, what is the probability that a patient in the ICU will become deceased within the hospital setting using static and demographic features, but also medical diagnoses and topics from clinical notes? So why do we care? Well, there is a plethora of literature on predicting mortality rates. And if we can use EMR data to have quicker feedback loops and create a model that can predict mortality, the idea would be to help prioritize and improve clinical decision making, especially if the models that we build are better than like the LACE models or a lot of the risk models that we see that is primarily rules-based that clinicians use currently. And really the topic that we wanted to explore in this project was, can unstructured data be helpful, right? Like we get a lot of structured information in the EMR when a patient goes to the hospital, primarily, their insurance status or their gender, and then also, what medications they're taking, lab results, previous admissions. But there's this potential large, just unstructured data that comes from medical notes and medical charts that doctors and other health professionals will write in the EMR. In the EMR, and it's really hard to use that data because it's unstructured and there's a lot of it. But with better technology and quicker feedback loops, and just more advanced computing power nowadays, it's now become possible to mine those medical charts and notes to find potentially useful features. And so the thing that we will do here is perform topic modeling, or LDA, on the clinical notes to hopefully extract meaningful features that are indicative of mortality risk in the ICU setting. So now we're going to go into some brief review of existing literature. So the paper that most resembles ours is Gassemi, who wrote a paper in 2014 that looks at predicting mortality using notes from the ICU setting. And interestingly enough, he basically fits models using LDA and extracts about, I think, like 100 topics from medical notes, and then he used those as additional features within his model and achieved about an ROC area under the ROC curve of about 85.85. I think that's so the project here that we'll do is motivated by a couple other studies here. So DeSalvo in 2005 provides a pretty interesting baseline model by basically predicting mortality using a question, basically like almost like a health outcome survey question. So health outcome survey is a survey that is given by CMS, and they typically ask questions like, how do you feel compared to last year? How is your mental health compared to, or how is your physical health compared to last year? And the patient answers, worse, very worse, or, better, or a lot better, and DeSalvo basically creates, a baseline model of mortality using those kind of questions. And Ciantis in 2011 just, there's been a plethora of literature about mortality, and he created just like an overall survey study, just which is linked in our reference section, to get just a general sense of like what other people have done in the field around mortality prediction in the hospital setting. So just getting into the data, so we use Mimic 3. So this is stands for Medical Information Mart for Intensive Care. It's maintained by MIT, and it comes from Beth Israel Medical Center. So it contains about 40,000 patients, 60,000 admissions, about 6,000 mortality events from 2001 to 2012. And we get a plethora of data. We get structured and unstructured data, right? Like there's static and demographic features. We have vitals, clinical notes, diagnoses, prescriptions, past utilization. And all of this is just a trove of data that we can use to try to predict mortality. And so just to get into some of the descriptive statistics here, we can see in the data that the mortality rate in our population is about 12%. This seems, of course, we do expect a decently high mortality rate, since patients in the ICU setting are inherently a lot riskier than normal patients. But we can also see that if we just look at admissions distribution, most of the patients here were admitted once. There's a long tail, as you might expect, of, there's this one patient that's been admitted 42 times, these so-called frequent flyers into the hospital system. But most of the patients were admitted once with a pretty right skew. On average, patients were admitted for about 10 days, with the median closer to about 6.5. Again, suggesting a pretty large skew in the length of stay in the hospital. And then one thing that I found very interesting when we look at the descriptive stats here is that the modal patient here is a Medicare patient. Next, and at about 48%. Then we have people who are on private insurance at about 38%, and then Medicaid comprises of about 10%. The last government, I guess, if you think about government, Medicare, Medicaid, the last remaining piece is typically the VA or Veterans Affairs, and that's about 3% of the population. And I think that makes really interesting to me, because Medicare patients do reflect a higher risk. They are typically older patients with chronic conditions and battling lots of comorbidities. And so it makes sense that in this data set, and for the hospitalizations, we see the modal patient is actually a Medicare patient. And I think this was interesting also because it turns out that when we just looked at static and demographic features, as we'll get to later on in the presentation, age and insurance type actually are pretty indicative features of mortality. And you get, a lot of good information just from that alone, actually, as it turns out. So before we get into the model and model results, I just want to talk a little bit about tech stack that we use and our extract, transfer, load process. So we have Python runtime. We use Hive and Hadoop. We have an H-based data store. And we ran locally to the machine. We did not use a hosted service like AWS, EMR for cost purposes. But we can, of course. We certainly can, and we were looking into it. So the configuration of Hive plus Hadoop was tuned to the available machine, and we use local. We just use like the local default settings, and the full run of pipeline had increased parallelism to utilize resources quicker. So more specifically, the pipeline was modeled as a set of scripts to run. If you look at our code that is submitted, you'll see like we have a script that's a pipeline runner, and you can run. It's basically just like run a series of files in order, a script in order. So it starts with some extract, transfer, load, or ETL of CSV files into HBase. Then we extract features into HBase tables via HiveQL. HBase tables are transformed to pandas data frames via HiveQL. And then finally, once we're done with the ETL process, what we do on top of that is we run some machine learning models that are built on scikit-learn or Python. And then we exported our best model, which ended up being a random forest model, as a pickled scikit-learn object. Okay, so we're going to get into the empirical design now of the project. So we just kind of talked about the data and our ETL process, and now we're going to actually talk about our model and what did we do in the actual model, right? So this table is, you can also see in the paper, but it's just it's a set of, it's basically just like the features that we use. So you can see here, really we ran three different models, and this is also motivated. If you recall earlier in this presentation, we talked in our literature review, 10 years ago, 15 years ago, when computing power was a lot less. We had a lot of papers that were coming out predicting mortality based off just a limited set of features, or even just like a couple of socio-demographic like questions or survey questions, right? And so really what this first thing is doing, this first model, I really just wanted to create a baseline model just based off demographic and static features. How much better can we do than random just off of very simple features that we basically can get in any EMR system, right? So this includes age at the time of admission, gender, ethnicity, admission type, insurance type, right? And I just found this super interesting, just to give us a baseline comparison, right? And as we add more clinically relevant features and clinical notes, how much improvement do we get on top of these demographic and static features? And so for clinical diagnoses, the other thing here, so our next level model on top of the demographic and static features is we also use clinical diagnoses. And it's actually very important here because we use ICD-9, or that stands for International Classification of Diseases, ICD-9 codes as features. But if you recall, there's actually about 65,000 different ICD-9 codes. Turns out that ICD-10 codes were introduced in October of 2015 in America, at least. But this data set was built using ICD-9 codes, and even ICD-9 codes, which are smaller than ICD-10, still have about 65,000 codes. And since we only have 60,000 admissions, just straight using ICD-9 codes would basically introduce a ton of a lot of variance, just a very sparse data set if we use all the ICD-9 codes. So here what we did was we actually grouped the diagnosis codes into higher level categories using clinical classification software codes that were actually produced by HCUP, which is Healthcare Utilization Project, that was underneath AHRQ, which is a federal agency within Health and Human Services that basically produced these higher level clinical codes that are basically a many-to-one mapping from ICD-9 codes. And so from here, it basically reduced the data set from 65,000 diagnosis codes to about 200 higher level clinically meaningful clinical classification software codes. And for our features, we basically just one-hot encoded them. So it's a 1 if the patient has the diagnosis that maps to the CCS code during the admission, else 0. That was the second model. So basically we used demographic and static features. On top of that, we threw in clinical diagnoses and we tried to predict mortality. And then finally, our best model or our most substantive model is using clinical notes. And that's really the meat of this project, which is, can we extract unstructured data from clinical notes using topic modeling? And in this case, we use latent Dirichlet allocation, and the scores produced by the LDM model from the notes associated with each admission. Right, and we basically use the score. So we have we extracted 10 topics, so we limited it to 10, and we had basically the scores returned by LDA of how relevant each topic was to the admission, and then we use that as additional features on top of demographic, static, and clinical diagnoses. So so just to rehash what I said before, the diagnosis data here, ICD-9 codes, 65,000 total codes, but we only have 60,000 admissions, so that would lead to sparse data, so that's why we use CCS codes. And then for LDA, again, we performed LDA on note events. So note events is one of the tables that is provided in the MIMIC dataset to extract topics from notes recorded during the admission. And in our use case, we extracted only a total of 10 topics because we felt that was kind of like an intuitive way to look at, to basically reduce the dimensionality. We didn't want to make it too sparse. We actually validated these topics. It turned out something pretty interesting was we actually spoke to a doctor, a geriatrician, who kind of looked over these topics to kind of provide us a little bit more clinical sense to what is being returned by the model. So just to give an example of topics returned by LDA, you can see here, right? So the way LDA works is LDA returns topics that are comprised by words associated with each document. So in this case, each document was a chart in the EMR of the MIMIC dataset. And what it did was it basically looks at these charts and finds, what are topics composed of the words weighted in a meaningful way. as it's just like a very base, high level description of what LDA is doing. So you can see here that just examples of the topics that are returned by LDA. So this first topic here, right? The words are contrast, mass, head, image, brain, right? And so here, we talked to Dr. Kumar Demarjan, a geriatrician who both me and Avi actually work with at Clover Health, to provide some clinical context on the topics here. And so contrast, mass, head, image, brain, right? It was a CT, basically the chart was about a CT scan about brain cancer. And so that was really interesting. The second and third topic here you can see are, like spine, cardiac, image, cervix, and basically, each of these really just correspond to a clinically meaningful context. And by talking to a doctor, it was just very reassuring that our model was just picking up things that made sense and are relevant when we're predicting mortality. So to get into the actual model itself, we ended up using a random forest classifier. So and we chose a non-parametric model such as a random forest classifier because we weren't sure necessarily, we definitely don't want to use anything parametric or that assumed a form because we imagined that there's actually high interactions and non-linearities that are relevant to mortality. So a random forest classifier just picks those up naturally. And what we did was a standard 70% train and 30% test split, and the metrics that we used were area under ROC curve and the precision recall, both of which are important, especially, right, we don't want to just use accuracy because even though mortality is a relatively highly prevalent in this data set at 13%, there's still lots of class imbalance here. And then recall that AURC, right, is really just another way to interpret it, which I find very interesting, is the probability that the model ranks a true positive over a true negative. And so we're going to get into the three different models, starting with the baseline model, and then going into the baseline model plus diagnoses, and then adding in clinical notes as well. And we're going to look at the different performances here. So that's going to be, that's what we're going to talk about next in this results section. So just to review, the main outcome variable that we're trying to predict is whether mortality was recorded in the hospital event after the admission. And so we present the results from three models. We're going to start with the baseline model. Uses age at admission, gender, insurance, race. Then we're going to get into the baseline plus clinical diagnosis data. So that includes all the features from the baseline model, but also uses diagnosis data. And then we're going to go into baseline plus clinical diagnosis plus clinical notes, which includes all the features from baseline and diagnosis data, but then also uses abstracted topics from the note events data using LDA. So this is actually pretty interesting, right? Like we first fit a random forest model that's just the baseline, age, demographics, and turned out because we basically one hot encoded these values, age, gender, ethnicity, race, insurance type, it ended up being about 100 features already, as it turned out, because I think there are like 5 different insurance types and like a bunch of different ethnicity types, race types. And you can see here actually the area under the curve is already about 70%. Right, so just using these static demographic features, right, and it turned out here, we actually don't show it here, but it turned out here that, like I said before, that the important features ended up being age and insurance type, right? Like just knowing the age, knowing how old someone is when they go into the hospital and whether they're insured or not, whether they're under Medicare or not, right, already has like a pretty like decent predictive power on predicting mortality within the ICU setting. Area under the precision recall curve is a bit lower at 18%. And again, remember that for the area under the ROC curve, the base, like just random luck would be 50%. For area under the precision recall curve, random luck would basically just be the class prevalence. And then remember, as we saw before, we saw mortality rate about 12%. So the area under the precision recall curve being about 18% is just slightly better than that. Okay, so that's super interesting. That provides us a decent set of just like how we do just using the general static features, like nothing that is directly clinically relevant. So now this next model here what we go over here is now we look at the baseline plus clinical diagnosis data, and I found this actually very interesting. When we use the CCS codes, when we use the higher level clinical classification software codes, the model performance actually improves a lot, right? It goes from 70% AURC to 83%, right? And so remember, what does that mean? It means that for someone who actually dies in the hospital, the model ranks their score higher than someone who doesn't die in the hospital 83% of the time, which is actually pretty high. In fact, if we looked at some of the external literature, 83 AURC is actually pretty on par with what's being published and what's written. Like Gassami in 2014, a lot of his models were really around like 83, 85% AURC actually. And precision under the precision recall curve, you can see it almost doubled, right? Like the model performance almost doubles to 36%. And I think actually I was playing around with this before, or when we're developing, really the motivation for using the higher level diagnosis classifications was because, when you just use ICD-9 codes and you just have a really sparse matrix, variance of the model just really just gets so high. And so, if you were to run this model with just the diagnosis codes without doing any more clinically meaningful higher level groupings, you actually get much worse results. And it's just so interesting to me that just like reducing that variance and reducing the sparsity by using clinically meaningful codes like really do result in a very big increase. And so this last model here, we also found very interesting. So this is now using the baseline plus clinical diagnoses plus the clinical notes, right? And what we see here is that the AUROC is about the same, but the area under the precision recall curve is a lot higher. It actually jumps to 42%. So this is our best model. And here, this is actually kind of interesting, right? Because now what you're getting at here is, how much additional value does the unstructured data add on top of the structured clinical diagnoses, right, already being captured? And what we see here is under the AURC, the improvement is slight. It's not that much, but then under the precision recall curve, actually, it jumps up a bunch, right? And you can actually see really if you flip flop back and two, really what it's doing is, if you look at the area under the precision recall curve, the curve actually is mostly pretty similar, except for at the very beginning, right, when recall is a lot lower. At sort of the left side of the plot, you can see precision is jumps really high, and so this is interesting. This is telling me that in the cases where we're relatively confident with just clinical diagnoses, adding clinical notes on top of that really makes us more confident, right? There's basically like a set of cases that where we're semi-confident with the clinical diagnoses, but then adding the unstructured data from clinical notes, there's a set of cases where we're even more confident and we can get even more precise about the patients who we think are going to experience a mortality event within the admission. And I think that's pretty interesting because if you look at EMR data, right, like a lot of the times the whole purpose of structured data in the EMR is to capture is for doctors and health professionals to capture what they're seeing with the patient in a structured format. So when we look at diagnosis data, right, like everything, a lot of the times, like the things that they write in the chart is also already going to be captured with the diagnosis data that they're going to code. And so to me here, I think this is interesting because there is a set of cases where our clinical notes and unstructured data did help. It seems like it didn't help, certainly the gap isn't as big as, the difference between baseline and clinical diagnosis data. But it did help in a certain number of cases. And I thought this was really interesting. And I think, moving forward, kind of as we wrap up and we think about future considerations, it would just be really interesting to just dive into this more, like really understand the cases where, what exactly are the cases where unstructured data adds a lot of indicative power even if in the general case, it's not adding that much, right? Because we did see this jump in the precision recall curve. So just like really understanding that more, right? And so I think just to wrap all that up, what we found was that just using static and demographic features provided some decent predictive power, like definitely better than random. Like just knowing the age, the time of admission, along with the insurance type, you just said a lot about the patients, which is definitely very interesting. The model definitely improves with diagnosis data, improves some with clinical notes. And I think really the next step here would be to talk with clinicians, improve the interpretability of the models to make it actionable in a clinical setting. And one of the really exciting things for me and Avi is that we also work at a Medicare Advantage plan, Clover Health, where we actually do have doctors and we have a clinical practice within our health plan. And so this is actually really exciting for us because we actually have a way to operationalize this in a real business context. So that's all that we had for our presentation today. Thank you so much for listening. And we're definitely looking forward to continuing this work even outside of this class. Thank you so much.